Okay, greetings to my dear student friends. We'll continue our module 2, that is to get the slopes and deflection of the flexural members, that is beams and frames. In this slope and deflection, we have covered the chapters like double integration method, Macaulay's method, moment area method, conjugate beam method. Now, we will continue the energy method, how to use the energy method to get the slope and deflection of the flexural members. This energy and work done, these terminologies are not new to you. Already you are very much familiar with these terms in your physics, high school physics, engineering mechanics, mechanics and material. Now let us refresh that conceptual definition. How can you use that to solve the beam problems? Okay. So if I imagine a beam, when it comes with a set of the external loads, we all know it deforms, it gives some deformations, and also it develops some internal forces in the member. Those internal forces are represented in the form of axial force, bending moment, and shear force. These axial force, bending moment, shear force with these internal deformations develop some strain energy. Similarly, the external loads for this deformation also develop some work done. The concept is the work done due to the external load and the deformations is equal to the strain energy due to internal forces because of those deformations, same deformations. They are equal. So that concept is used to get the deformation, that slope and deflections. That means here the relation between the external load and the internal forces, and you are using the concept of the energy to get the slopes and deflection. So in this concept of energy, there are among the multiple methods. The first method what you will learn, that is strain energy method. So to use the strain energy method, let us have some brief idea. How can you compute the strain energy for the different internal forces and the deformations? If the internal force is a direct load, axial load, we all know, or if you don't know also, these expressions with figures will help you to understand how can you calculate this energy from the axial load, that is p square L by 2ae. Each line is self-explanatory, so I will not take much time to explain you in detail. Similarly, after axial load, if I look at the flexural load, that is the bending moment. If bending moment is the internal force in a beam member, then correspondingly it will develop some slopes. Because of the bending moment, the corresponding load is the corresponding deformation is the slope. Okay, so that slope and bending moment, all these expressions you know in your double integration method and moment area method. By rearranging those expressions, we are computing the strain energy. Okay, that's strain energy, and the geometrical behavior, the geometrical variation of the force and deformation moment and slope, they are all shown here. That I will not take time to discuss that in detail because they're self-explanatory. So if I use the moment and the slope, then my expression comes out here like this, that is m square L by 2ei. And this expression also can be expressed in differential form, that is L, if I put a small distance dx, then I will put an integration over the region, that is m square dx by 2ei integrated over the length 0 to L. The segment, for which segment we are computing the strain energy, for that segment length is integrated here. Okay, so the expression is m square dx divided by 2ei integration over the segment length 0 to that distance. Okay, now similarly you can also calculate the strain energy for the shear force. This expression is derived. Similarly, you can also calculate the strain energy for the torsion as well. But for your beam problems, the predominant force is the bending moment. The strain energy due to bending moment is very much significant, such that this strain energy due to torsion, strain energy due to shear, and strain energy due to axial force can be ignored. So that's why among all the internal forces, for the beam problem or the frame problems, we don't take into account the strain energy of other forces. Only we take strain energy of the flexural force, that the bending moment. So this expression is very much essential to get the slopes and deflection of beam or frame members. So next we will solve an example to demonstrate this expression. This strain energy also alternatively called as a real work done method. Is also sometimes is called as a real work done method. So in this real work done method, already I have expressed this expression. Strain energy is equal to real work done, and this is the work done expression, and this strain energy expression the U is equal to, that's what you have seen in before, m square dx by 2ei integrated over the segment length. That's the length of the member. Okay, now let us take an example of a cantilever beam having point load at the free end to get its deflection. Okay, as you understand the expression already, now let us calculate two terms. One is the external work done due to load P, and what is the strain energy due to this loading system. So we know the strain energy expression is m square dx by 2a over the length 0 to L. So what is m? M is nothing but the bending moment. To calculate the bending moment at any arbitrary section for this cantilever beam, if I take a distance x from the free end, then my equation is p into x. Alternatively, you can tell us minus p into x. If I take the sign into consideration for the calculating the bending moment, then it will be m is equal to minus of p into x. So here this minus is not given emphasis because at the end to calculate the strain energy, this term gets a square. That's why this sign is not taken into account. But for you, if you want, you should take the sign into account, because here it is a single point load. When there is a multiple point load and the direction of loads are of different kind which contributes in the sign convention, then we cannot ignore that. Here it is a single load, so this ignorance is fine, but when there is a multiple load forms, then ignorance of sign may mislead to a incorrect answer, may mislead to a correct answer. So for the single point load, we can calculate m is equal to px, and similarly you can calculate the strain energy state expression. Okay, and then we equate the strain energy with the external work done. The external work done is equal to half into p into delta. So you can raise a question in your mind, why it is half? Because this load what is applied here, we are assuming the energy what it is stored because of the internal process, it is not stored suddenly. It starts from a displacement. When it stores the energy, it starts from displacement 0 to reach its maximum. It takes the time. That's why it takes the average of that. And that's why from the load deformation curve we are getting this. Also keep in mind the strain energy, we are applying this for linear elastic structure. Okay, for the where the theorem of superposition is allowed, that those problems this concept is applicable. Similarly, this is another example of a simple supported case where the point load is applied at the center, and here the moment of inertia or the flexural rigidity is not uniform throughout the length. So for half of length is EI, another half of length is 2EI. So whenever you compute the strain energy, you should keep in mind, because EI is a major role for computing the strain energy. So that's why for this part we will put EI, and for this part we will put 2EI. Again, for the given 60 kilonewton, you can calculate the reactions. After getting the reaction, here you can divide into two segments. So this total beam, let us put this is a half and this is another half. If I put this is point C, this is point A, and this is point B, then AC is one part and CB is another part. Like this, the strain energy calculated here. So for AC part and for CB part, the strain energy is calculated. If we look at the 60 kilonewton, then the reaction is 30 kilonewton here and 30 kilonewton here. Okay, so the bending moment at any distance x is equal to 30 into x. Similarly, bending moment at any distance x is equal to 30 into x. So that bending moment 30 into x is there, and here 30 into x is the bending moment for the left segment, this for the right segment, and EI is EI here, and this EI is equal to 2EI here. Okay, so after getting the sum of these two values, the total strain energy calculated here, and then the external work done half into P into delta, they are equal to be this to get the delta, the deflection at the center. Okay, but what you learn from the strain energy method is that the strain energy method or the direct work done method is not that versatile to use when there is a set of load is multiple, because here only